So welcome to tutorial 6. Let us see what are the problems that we will be solving today. So the first question is, so this is all related to character tables and reducible versus irreducible representation. So I know we have already done this, but let us look at it more carefully again. So reduce the following representation. So once it is saying that reduce the following representation, it means that it is already a reducible representation which you have to reduce into component irreducible representations. Okay, so into there, sometimes it will say component species, sometimes it will say component irreducible representation. So either way the meaning is same, that you have to reduce it into component irreducible representations. Okay, so the given example is of the point group D3H, and the reducible representation is tau, and the corresponding elements or the operations are 2C3, 3C2, sigma h, S3, 2, and 3 sigma v. Now the characters are 5, 2, 1, 3, 0, 3. Okay, whatever is the basis that will come here, but we don't know what the basis is to create this reducible representation. Our job is to reduce this representation. So to reduce, now what we have to do is we have to write the irreducible representation, set of irreducible representations. So let me write down the character table first. So what we have here is A1 prime, A2 prime. I will not solve it completely, but I will just give you again how to solve it one by one, point by point. A1 double prime, A2 double prime, E double prime, right? Okay, so let me see that I'm writing all of this as 1111. Okay, and then there are other characters corresponding to other irreducible representations. Okay, so now we know that now this tau can be expressed as A1 times, let me write down the symbols, or let me just say A times A1 prime plus B times A1 double prime plus C times E prime plus D times E double prime plus E times A2 prime plus F times A2 double prime. The order does not matter. So idea is that this particular irreducible representation is a linear combination of all the irreducible representations. Now the coefficients, we have to find out all these coefficients. Some of the coefficients will be 0, A, B, C, D, E, F. Some of the coefficients will be 0, some of the coefficients will be real numbers. So they will always be real numbers. You cannot have fractions. So I will say A, B, C, D, E, F can take only integral values which are positive and 0. It cannot take fraction. So that is a test whether you are getting these coefficients as correct numbers or not. So the test is that they will always be, so basically it's a set of whole numbers starting from 0 towards positive infinity, right? So integral positive, so this will be whole numbers. So anywhere in whole numbers, this will take the value. So that is the test. That otherwise, if it takes negative value, for example, that means your calculation is not correct. Okay, all right. So let me just do one calculation for A1 prime, and then rest of the calculations will be very, very similar. So let's see. So we know the reduction formula. So we will use the reduction formula. What does the reduction formula say? So reduction formula says any coefficient A will be equal to 1 over h. H is the order of the group, summation over all R, chi AB, chi A, let's say this is the reducible representation, and chi I, let's say this is AI. So this is for ith irreducible representation, and this will be multiplied by a factor g, where g is the number in front of the symmetry element. So that means it's the number of class elements or number of elements in that particular class. Okay, so this is number of elements in that particular class. This is very important, otherwise you will mess up the whole calculation. So this g comes here. So let's now see how it is done. So we'll calculate A, and rest of the calculation you can do as a homework. So 1 over h. So now h is the summation of number of all the elements here, so which is the order of the group. So it is 1, 2, 3, 4, 5, 6 and 6 more, so 12, right? So 1 over 12. So there are 12 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12 elements in the group, which are categorized into 6 classes. So we have 12 here. Now summation over all R, that means we have to take all the values of R. So R is changing from E to sigma V. So we have 6 different classes here. Okay, now chi A is the character under reducible representation. Let us say if this is A, so this is the character under reducible representation. Chi I is the character under irreducible representation, of which the coefficient we are trying to find out, right? And G is the corresponding class element, corresponding class size. Okay, now this would be, so I will take 1 from here. So this 1 into this 5 into this 1 over here. Then this 2, 2, 1. So 2, 2, 1. 3, 1, 1. So 3 into 1 into 1. Then I have 1 into 3 into 1. 1 into 3 into 1. Then this is 0, so it does not count. So I have 0. 3 into 3 into 1. Right? So this gives me 1 over 12. 5 plus 4 plus 3 plus 3 plus 9, which is, so 9, 9, 18, 18 and 6, 24. So this is 24 by 12, which is a whole number. So this is 2. So that means A1 prime will appear twice in this reducible representation, right? Similarly, rest of the coefficients can also be find out. So I will leave that to you. So complete this. Find out, find B, C, D, E, F in homework. So this course is all about calculation. So it would be better to do the calculation yourself by your hand, so that it is very, very clear in the head, and also the speed will also matter. So with the speed which you are doing the calculation would also matter in the exam. So sometimes if you are not doing it optimally, then it will affect your answering capacity or capability in the exam. Okay, so it is better to practice. It's a simple maths problem, so you should be able to practice. Okay, now let us look at second question. So far we have learned about character tables. We have not looked at character. There are some special groups called as cyclic groups, which we will learn in next week. So but I'm giving you a problem which has some component of cyclic groups. So let us say, but it is related to character table. So construct real number representations by combining the complex conjugate paired. So complex conjugate paired, I will tell you the meaning of this. Irreducible representations in the following point group. Point group given is C4. Okay. So there are some cyclic groups for which the character table is not real numbers or not integers, positive or negative. So there are some complex numbers always coming into those character tables. So let us see how the character table for C4 looks like. So C4 will have group elements as E, C4, C2 and C4 cube. And the character table is something like this. So A, which is all ones, totally symmetric representation. B will be negative with principal axis, 1 minus 1. And then there is a two-dimensional representation E. And then if you notice, you will see that there is a curly bracket written. So normally, so far, the character tables which you have developed, they don't have those curly brackets. But in cyclic groups, these curly brackets will come. And then we will also see that how great orthogonality theorem cannot be used to actually write these character tables. And then there is a separate method to do that. We will discuss that next week. But I'm just trying to give you an example of how those character tables look like. Okay. So you have 1, 1, iota, minus iota, minus 1, minus 1, minus iota, 1. Okay. And then this side also there is curly bracket. So this is closed in curly brackets, and then rest of the components of character table are same. So you have some unit vector basis here, binary products as the basis here written. Okay. Now the question is asking that construct the real number representations by combining the complex conjugate paired IR representations. So if you see that A is already a real number representation, B is already a real number representation, whereas E has complex numbers, right? So now these complex number would always come in pairs. So if I have a complex number here, I will have a complex conjugate here. Similarly, if I have a complex number here, I have a complex conjugate here. This is I. Okay. So how do I combine this? What I have to do is I have to just take the summation and write the character table like this. So E, C4, C2, C4 cube. The A and B part remains same because those are already real numbers. 1 minus 1, 1 minus 1. Now E will be written as, so if you take the summation of this, 1 plus 1 will be 2. I plus minus I will be 0, minus 2 and 0 again, right? Now I don't know here by just looking at this character table like this whether it's a summation of two complex conjugate pairs or not. So to indicate that, what I do is I will do a curly bracket here. Okay. So now my E is represented within the curly brackets. So that means this E is actually not a independent real number IR representation. It's a two-dimensional representation, but it is composed of complex numbers and complex conjugate paired IR representations, right? So all you have to do is you have to just take a summation and write down the number which comes as a result. Okay, let's do one more example of this so that there is no doubt. Let's look at one more character table like this. So I'll take a simple one, C3. So you have E, C3, C3 square, and I have A here as 1, 1, 1, and E is written as complex conjugate pair. So I have 1, 1. And now if you see, you have written epsilon, epsilon star. So this epsilon is a complex number and epsilon star is the complex conjugate of that, and epsilon star and epsilon. We will see what is the meaning of how do we write these epsilons. So in the character table itself, epsilon will be defined and it is written as exponential 2 pi I by 3. Okay. Now what does it mean? So this means if I'm writing it as exponential 2 pi I by 3, I can always write it as, I can expand it in terms of, so this is nothing but E I theta. If 2 pi by 3 is theta, then E I theta. So this can be written as cos theta, which is 2 pi by 3, which is the real part of this complex number. And the imaginary part can be written as iota sine theta. Right? So epsilon means this, and epsilon star will be cos 2 pi by 3 minus, so it's a complex conjugate of this, so whatever is the I coefficient that goes negative, I sine 2 pi by 3. Right? So now you know the values. So now this character table can be transformed into real numbers, and what we have to do is you have to just take the summation of these two vertically. So E C3 C3 square A 1 1 1, and E will be now written in curly brackets 2. Now if you take summation of epsilon and epsilon star, your iota will get cancelled and you will get only real number, right? So this will be 2 cos 2 pi by 3. Similarly here also it is epsilon plus epsilon star, so this will be 2 cos 2 pi by 3. So this representation and this representation are same. This is the real number equivalent of the original character table. So sometimes in calculations you need real numbers. Let's say if you want to calculate the irreducible components of a reducible representation, then you would need this, and you cannot do the calculation with complex numbers. So that's how basically you convert it into real numbers and then you do the calculation. So let us see our next question, which will deal with that. So I hope this is clear. If not, please shoot me an email. So third question is, reduce the following. So we will be doing lot of this. We'll be using lot of these results, reducing the reducible representation into irreducible representation when it comes to application of group theory into chemistry. So it will be better if you do this practice now itself, okay? Because this will be used as an exercise, like as a passing by comment that, okay, by using reduction formula, we get this. But how to do this is taught here. So later on in the later parts of this course, the results will be used directly, okay? So it will be better if you practice a lot. So reduce the following representation from groups whose irreducible representation contain imaginary characters into their component species. So now let us first write down C5. We have E, C5, C5 square, C5 cube, C5 4, and our tau A is 7, 2, 2, 2. Okay. And if we now look at the character table, the characters are like, so for C5 I have A, which is all 1, and then I have E1 and E2, and these are complex conjugate pairs. And what I have here is 1, 1, 1, 1. Then I have epsilon, epsilon star. Now here I have epsilon square, epsilon star square, or epsilon square star, whatever, does not matter. Epsilon star square, epsilon square, epsilon star, epsilon, right? And here also there will be some character similar to this. So now let us look at the linear combination of tau A. So the linear combination of tau A should be A times A, B times E1, C times E2, right? So let us try to find out what is the component for E1, okay? Because we are interested in looking at the complex numbers calculations, right? So also epsilon here will be given in the character table as will be equal to exponential 2 pi I by 5, okay, because it's a C5 group, so 2 pi by 5. All right. So now if I take the summation, I'll have to convert, to be able to use the reduction formula, I'll have to convert this into the real numbers. Okay, so for real numbers I'll have to take a summation of this. So when I take summation of epsilon and epsilon star, I will get 2 cos. So epsilon plus epsilon star will give me 2 cos 2 pi by 5, which is the real number. Now for square of this, if I take a square of epsilon, that means my theta will become 4 pi by 5, right? So epsilon square will become exponential of 4 pi by pi I by 5. That means if I'm taking epsilon square plus epsilon square star, this will give me 2 cos 4 pi by 5, right? So that will be the difference between summation of epsilon and epsilon star and summation of epsilon square and epsilon star. Okay, all right. So now that would mean that the characters which I have as real numbers will be A, E1 and E2. So A will be all ones, this will be 2, and this will be 2 cos 2 pi by 5, this will be 2 cos 4 pi by 5, 2 cos 4 pi by 5, and 2 cos 2 pi by 5. So now that you have all the real numbers, so you can use the reduction formula easily, right? So let us do one calculation for E1, and for A and E2 you can do the calculation at home. Okay, so let's quickly do this. Okay, so for B component, so the order of the group is 5, and what I will have is, now the class size is 1, then I have 7 coming from the character under reducible representation, and 2 coming from the character under E1 representation, right? Then similarly I have 1 into 2 into 2 cos 2 pi by 5, 1 into 2 into 2 cos 4 pi by 5, 1 into 2 into 2 cos 4 pi by 5, plus 1 into 2 into 2 cos 2 pi by 5. Now you would need calculator for this, because this becomes cos 72 degree, this becomes cos 144 degree. The values I don't expect you to remember, but if we do the calculation, what I have is 14 plus this will become, let us combine this and this, so you will have 8 times cos 2 pi by 5 and 8 times cos 4 pi by 5. Okay, this is simple combination, and this becomes 1 by 5. 14 plus 8 can be taken out, so cos 72 will be 0.3 and cos 144 will be minus 0.8, and then you will get minus 0.5 here. So what I have is 1 by 5 14 plus 8 into 1 by 2 with the negative sign. Now this cancels, so you have 10 by 5 and that means 2. So that means your tau A will contain at least twice the E1 representation, right? Similarly, you can calculate for coefficient of A and coefficient of E2. So now you should be able to do this calculation, rest of the calculation, please. So tau A is A times A plus 2 times E1. This 2 is coming from here, which we have determined, plus C times E2. So I have shown you how to determine this B. Now try to do this same calculation for finding A and C. Okay, so that will be your homework for this tutorial. Okay, so the question says that in C3V, both C3 and C3 square belong to same class. This you already know, right? And that is listed as 2C3 in the C3V character table, right? Now, because these are members of same class, so their characters are same under different representations, right? So now the question is saying that demonstrate. So there are two parts to this question, demonstrate. So first part is demonstrate that both C3 and C3 square, which are of the class 2C3, have a character 1 for the A1 representation. Okay, and second part is demonstrate that both C3 and C3 square have a character -1 for the E representation. Okay, so to do that, let us first write down the character table of C3V point group. So you have C3V E 2C3. Now this 2C3 is saying, they are saying that C3 and C3 square both belong to this class, and 3 sigma V. So you have A1, which will be 1 1 1. Now both the characters of C3 and C3 square are 1, right? A2 1 1 minus 1, and for E it is 2 minus 1 0. Now if we also list down the unit vectors, I have Z RZ, then XY, and then Rx Ry. Now the meaning of this is that Z transforms as A1 and XY transforms as E. Okay, now we want to write the characters, we want to demonstrate that the characters of C3 and C3 square under A1 is 1 for both of them, and for E it is -1, right? To do, what you have to do is you have to simply write down the transformation matrix for XYZ under C3 operation and under C3 square operation. So for C3 operation, so let us first write down any general operation for C and Z. So this will be, we already know that cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. So this implies that C3 will be, now the angle will be 2 pi by 3, right? 2 pi by 3 is 60 degree. So you have cos 60 minus sin 60, 0, 2 pi by 3. Now this will be 120 degree, sorry. This will be sine 120, cos 120, 0, 0, 0, 1. Okay. Now this is for C3. Now if you see that this is block diagonalized matrix, right, in this form, in 2:1 form. So that means the x and y are jointly transforming as the upper part of this matrix, whereas the z is transforming as this. So the character for z basis will be 1 here for C3, and character for xy, that is E representation, will be summation of cos 120 plus cos 120. Now the value of cos 120 is minus half. So what you have here is minus half, and this will also be equal to minus half. So the character for C3 becomes minus 1 if you take the summation of these two, because the character or the trace of the matrix goes here as the character. So trace of the matrix is obtained by summation of diagonal elements, and we will take summation only up to here because Z is a separate representation, which is A1, right? So this part is a separate representation corresponding to A1. This part is corresponding to XY, which is E representation. So that means character for C3 under E will be minus 1. Character for C3 under A1 will be 1. Now for C3 square, how do you get the character for C3 square? Now C3 square can be understood either by changing the angle or by changing the sense of rotation. Okay, so we know that C3 square can be thought of as an inverse of C3, or we can write, if we take inverse here or inverse here, does not matter. So C3 inverse can be taken as C3 square. Now what do you mean by C3 inverse? So you can actually calculate the inverse of this matrix, or what you can do is make the rotation as clockwise. So this is the matrix, or this is the matrix for anti-clockwise rotation, right? So for a clockwise rotation, you can write C and Z. C and Z is equal to cos theta sin theta 0 minus sin theta cos theta 0, 0, 0, 1. So this is for clockwise, and this was for anti-clockwise rotation. So what do you mean by that? So C3 and C3 inverse are related by clockwise versus anti-clockwise relation. So if you are saying that this is my matrix for anti-clockwise rotation, and I want to obtain the matrix for C3 inverse, so C3 inverse can be written as C3 when done clockwise, right? So I can say that the negative sign from here will go here, which will not change the character, because the character is coming from this part, which is still the same, right? So cos 120 is still the same as minus 1. So that means the character for C3 square and C3 will remain as same, right? So I hope it is clear. If it is not clear, so then you can also argue that C3 square can be considered as the angle can be changed to 240 degrees because it's twice the rotation. So if you do cos 240 minus sin 240, sin 240, cos 240, you will still get the same result, right? So basically the idea is that these two, summation of these two will give you character under E. This character over here will go under A1. So that is all for today. I hope these tutorials are helping you do some calculations and some practice sessions at home. So, all right. So see you next week then. Thank you.